Alrighty. Hello, everybody, and thank you for joining us today. Welcome to today's topic, primary injection on low voltage circuit breakers, what, when, and how. My name is Griffin Cannell, and I'm a digital campaign manager for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter team. On the left side of your screen, you will see the Ask a Question window. You can submit questions at any time during the presentation, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, your certificate of attendance, a copy of the presentation, and a link to a video recording of this webinar will be sent to everybody in about 2 business days. Our presenter today is David Martinez, Substation Application Engineer. To assist with the question and answer session, we'll also have joining us Nadozi Iranini, Substation Application Engineer, and Swapno Murati, Substation Application Engineer. With that, I hand things over to our presenter. Thank you for joining us today, David.
Thanks, Griffin. Hello, everybody. My name, again, is David Martinez, Application Engineer with TSG. And again, this presentation is going to be over primary injection on low voltage circuit breakers, what, when, and how. So in today's presentation, we're going to be going over some theory as far as what primary injection is, giving some understanding behind the breakers, as well as the theory behind the reason we test. We're going to take a look at some of the historical advancements and challenges faced when doing primary injection, as well as how to test, some industry hurdles, understanding time current curves, and when to perform testing. So when you should test and looking at signs of degradation. And we'll also have a few slides at the end highlighting Megger's newest primary injection test set. So what is primary injection? So in order to understand primary injection, you need to understand breakers. So breakers themselves are dumb. They typically need a brain to operate. So that brain is going to be your trip unit. So why should you test? You're testing in order to verify the operation of that trip unit, as well as verifying the mechanical integrity of the breaker itself. Typically, you'll test to the time current curve that you'll find in the breaker manual, so you can make sure it trips when it's supposed to. In this presentation, we're only going to be talking about low voltage circuit breakers. So we're going to be ignoring medium voltage circuit breakers and high voltage circuit breakers, okay? The two types of low voltage circuit breakers will be your molded case breakers and your airframe breakers. Molded case, again, are going to be in that insulated plastic material. And typically with those, they're rated to the frame size to where they can handle the current that's going to be pushed through them instantaneously. Same thing for your airframe breakers. It's metal housing. Air would act as the insulating material in that one. So now we'll take a look at a few low voltage circuit breaker characteristics. So again, you'll have your frame, whether it's metal or molded insulated material, and then you'll have your trip unit. And the trip unit can be a micrologic or solid state trip unit, or it can be a thermomagnetic trip unit, as you'll see in a lot of smaller molded case breakers. And so the way your digital trip unit would work is pretty much you'll have CTs wired into the trip unit, and as current passes through, if the CTs see an increase in current to a certain threshold, then it'll cause it'll send a message to the trip actuator in the breaker, and it'll cause the breaker to trip. Whereas on the right hand side, if you have the thermomagnetic component, it's basically a bimetallic element or strip of metal inside the breaker itself, and it's basically composed of two different metals that bend at different rates. So as it heats up, it'll bend and it'll hit and cause the latch to open, and it'll open the breaker. And then you also have the magnetic element seen on the right top, which is basically just a little coil. So when the current gets really high, it'll energize that coil and draw the trip bar to it and cause the breaker to trip. Now, when testing breakers, you typically test to whatever the rating of the breaker is. So seen here in the picture, you'll see a 1600 amp frame size breaker. Now, breakers can be derated, and when you derate a breaker, typically you'll put in a sensor plug. So sensor plugs are removable, and they're used to, again, derate the breaker. You can always derate a breaker, but you can never make a breaker higher than what its frame rating is. Here we have a typical airframe power circuit breaker, and we're just going to take a look at the few components that we can see here. So on the left-hand side, you have the breaker terminals. So these are useful when you're trying to overcome ground fault when trying to test other functions of the breaker. So you can typically short certain terminals. You'll also have the trip unit here in the center. That's where you're going to make all the changes you need in order to get the test current the test current and get the breaker to operate how you want it to when installed. You have trip indicators seen here. Those typically will be poked out whenever the breaker trips on a certain setting, and you can reset those just by pushing them. You have a nameplate seen in the top right. Spring charging mechanism, for that we have the lever. We have a trip and a close button. Trip, again, is going to manually trip the breaker. Push to close is after you've charged the spring, you'll close the breaker. You have the racking mechanism, again, used to rack in, rack out the breaker in switchgear. So now taking a look at the molded case breakers. Typically with these, you always want to look at the nameplate when looking at the rating of the breaker. So again, the nameplate highlights what the rating of the breaker is, as well as the breaker terminals here. Breaker terminals, again, is where you're making your connection with whatever primary injection test set you're using, or if you're performing other tests on the breaker. Here we have another look at a larger molded case circuit breaker where you can see the trip unit as well as a rating plug inside it. So again, that rating plug, it's making it act like an 800 amp breaker. It's still the same as what it's rated for, 800 amp frame size. And you'll see this one has short time pickup on it. It doesn't have any other settings that you can adjust. So typically most breakers will always have a long time and an instantaneous setting that you would test. But on this one, the only adjustable one is going to be the short time. Here you look at a few other trip units that you'll see. So on the left-hand side, you'll see a trip unit that has pretty much options for you or dials for you that you can adjust on all the LSIG settings. And on the right-hand side, again, a more complex trip unit. This one we're actually going to be taking a look at later when we go through an example of how to run through a test. So when testing breakers, you want to test the essential elements of the breaker. So going through those, we have the operating mechanism. So for that, again, you're making sure that when the breaker exceeds or when current exceeds the breaker rating, it's going to cause the breaker to trip. So for that, you want to make sure that it's properly lubricated and that you exercise it, especially when doing timing. So the more you test, the better your times will come out. And so typically you want to exercise that, make sure that the mechanism's correct, making sure that everything's within tolerance. There's nothing wrong with the spring charging mechanism or anything like that. Another element of breaker testing or the breaker itself is the conducting path. So to test this, typically you're going to be testing with the DLRO or doing a millivolt drop test with your primary injection test set. When doing this, you're actually testing the moving and the stationary contacts. So again, the main and the arcing contacts. When testing those, again, your condition is going to be determined mainly by your resistance readings, as well as a visual inspection. So checking if there's any burn marks, any damage to your contacts while doing while doing your visual inspection is very important. Another essential element is going to be the electrical insulation. So again, this is actually isolating the conductive path between each pole of the breaker. So you want to make sure that everything's properly isolated, that you're isolated from ground, that that you're testing the insulation between phases from phase to ground. So when doing that, you're going to be using insulation test or a Megger test. And then the last essential element that we're going to look at is going to be the trip device, which acts as the brain of the breaker. So when testing a trip device, you can perform one of two methods. You can test with either primary injection, which is injecting current through the primary current path, or secondary injection, which is verifying the response of the trip device using secondary injection. So a little bit of theory behind the test methods again. When you're testing the electromechanical integrity, that's when you're doing your contact resistance, your insulation resistance, and then you're actually manually operating the breaker. That's when you'll hear the term slow closing the breaker. You're just making sure that all the contacts check out, your insulation between phases checks out. And then when you're actually testing the control functionality of the breaker, you're performing either primary or secondary injection. You're testing the trip units of the breaker and the breaker itself, making sure that it adheres to the time current curve and that it tests when it's supposed to, depending on the dial settings for long time, short time, instantaneous, and ground. So we mentioned secondary injection. Typically, these test sets on the market, they're a lot cheaper. They're typically sold by the manufacturers of the actual trip unit itself. But these are only testing the trip unit itself. They're not actually testing any wiring and current sensors in the breaker. Now, the reason primary injection is more advantageous is because you're actually passing current through the CTs of the breaker. So you're testing the operation as well as the trip unit logic, as well as all the wiring and current sensors in the breaker itself, making sure that everything's correct. So that's what makes it a complete test. So again, why primary injection? It's really the only method to test all the functionalities of a low voltage circuit breaker, making sure that the operating mechanism, main contacts, everything's checking out, making sure that your terminal connections, everything's connected properly. And so the way we do primary injection, so seen here on the right, you'll have a two-phase molded case circuit breaker. So you have the frame, you have the operating mechanism, trip bar, connections, contacts, everything like that. So diving in, you'll see you pretty much just have your primary injection test set, and then you'll attach the leads to the line and the load side, and you're injecting across a single phase of that breaker. And so you're able to test each phase as you perform primary injection. Now we'll take a look at some of the advancements and challenges of primary injection test sets throughout the years. So we have legacy test sets. So seen here depicted, we have these big bulky test sets. Now these ones, the issues you had with these, again, are these things are massive, sometimes weighing upwards of 1,200 pounds or more. So shipping is always going to be a problem. Repairing is always going to be a problem. You also have input power constraints. Typically with those, they operate only off single phase supply. And so you have a lot of issues getting power from generators as well. Just because they're older, you run into a lot of issues with these. However, they are extremely reliable. So again, you can run into issues with size, transportability, manual reporting, and then just being too big. But again, you'll never go wrong with having one of these test sets. These test sets were reliable. Again, everything manual as far as the variac, tap changer, everything like that. So very easy to teach on. Just again, not really transportable and not ideal when you're trying to get into those small switchgear rooms or into the data centers with these. So the next advancement again is adding a PLC or automated timer. So with this, the control is made more kind of automated to where you can find, request your current, set timers and everything like that. Again, you still have the size constraint. You look at these things, they're a huge, pretty much metal frame, 1,200 pounds. And again, it's still to the point where everything's still manual in regards to reporting and operation, and the training on these is a little bit harder since they have that PLC control or programmable logic controller. So then the next step that we took in the industry was moving to smaller, medium-sized primary injection test sets. So these are addressing the portability issue, but they're also sacrificing the output current. So with the larger test sets, you're able to inject anywhere from 40,000 to 60,000, 80,000 amps. With these test sets, again, you're going to be in the smaller range, maybe 20,000, 10,000. So these can't fully functionally test the large frame breakers, 4,000 amp rated breakers and up. They don't have a curve library. So again, when you're testing breakers, you're testing everything in regards to that time current curve. So you're always going to have to flip through manually and look through the curves. And again, you have current regulation challenges to where throughout, you're going to have to try and you basically when doing primary injection, as your cables heat up and as you're performing current injection at higher currents, you'll have something what we call current decay. So basically, if you have your test current set to 2,000 amps and you're testing for a few minutes, you're going to see that amperage slowly drop to maybe like 1,950, 1,900. So you have to constantly monitor and ramp up the wheel to make sure you keep it at 2,000 and make sure your results aren't skewed in any way. So that is another issue with these older test sets that didn't have any of the software in them yet. So here we have a small range tester now. So these are real good for ground fault testing, testing smaller rated breakers, a lot more transportable and easily able to use whatever power supply you have on site. Again, with these, you're limited to smaller size breakers. You can't test your large breakers with these. You sacrifice the output current for portability. Here we have one of our newer primary injection test sets as far as in regards to adapting software into the testing now. So here you'll have digital curves and reporting capabilities. But again, you have wires, so you'll have impedance issues. Again, it's small, it can't fully test, your larger frame size breakers. So that's why you see here on the right, these ones were paralleled in order to test like an 800 amp breaker. So again, smaller size typically leads to sacrifice of portability. So we'll address, what Megger has to offer, at the end of the presentation. But now we're going to take a look at time current curves. So time current curves, again, what we've been mentioning throughout this presentation. Seen here pictured on the left is just showing you the different regions. So typically your long time and short time will correspond with your overload protection, and your instantaneous will correspond with short circuit protection. So we're looking here at a typical time current curve. The breaker trip curve is pretty much just showing you when the breaker is expected to trip at specific settings when you have them dialed in on that trip unit, whether it's a micrologic one where you manually program the current in, or when you put the delay in, or if it's on the dials where you have to go and refer to the manual. So there's several regions you want to look at. Again, you have your long time and short time. You have your instantaneous, which typically is going to be a horizontal line. And then you have your ground fault, which can appear on the same curve sometimes, or sometimes it'll have its own curve entirely. Now you'll see here we put 10% threshold. That's just a rule of thumb. So what we mean by that is you'll see on the trip curve, you have an upper band and a lower band. So depending on what those limits are, it can be plus or minus 10%, or it can be higher than that or lower than that. It's all going to depend on the breaker manufacturer and then what it says in that actual breaker manual for that trip curve. Because typically you can see different percentages. You can see 7.5% tolerance. You can see, 15% tolerance. It can change. So you always refer to the breaker manual for that. But again, these are used to verify breaker operation, and these aren't a logarithmic scale. So everything's not just eyeballing anything or measuring the scale or anything like that. It's in a log scale, and you'll see it pictured later in the couple of curves we have. So again, time current curve, we're looking at what each region means. So for a long time, again, it's your overload protection. So this, as an example, would be, and I guess that animation didn't work, but pretty much an example of that would be like if you had a water pump starting, right? You'll have a small increase of current. Your load will be a little higher for a certain amount of time. So you have long time protection in order to accommodate that and let that happen without tripping the breaker. Your short time protection, again, is protecting for medium increases in current. So an example of that is your inrush current from starting a motor. It'll spike for a really small amount of time, and then it'll get back to a steady state. So your short time allows for that to happen without tripping the breaker. Instantaneous protection is going to be protecting you from a high increase in current. So if you have a wire shorted between motor windings, for example, that's what that region is protecting you from. And then your ground fault protecting you against fault current flow in the ground. So now when looking at those specific settings for a breaker and looking at how you test those, so in your NETA testing standards, typically it's going to say minimum of 300% for long time testing. So what we mean by that is whatever your long time pickup current is, and we'll show you how to find that later in an example, you multiply that by 300% or 3 times. So again, you're going to be injecting continuous current, and then when the breaker trips, you're going to record that trip time, and you're going to validate that time according to the time current curve. For short time and ground fault, that's going to be done at 1.5 times, whatever the short time or whatever the ground fault setting is. And then you're going to see for both of those, you're again applying continuous current, and then you're going to record the trip time. Now, typically your ground fault, you can have delay, but typically that's going to be close to instantaneous as well. Your short time, it's kind of close to instantaneous as well, but you also have delays on that you can set on the trip unit. And then your instantaneous setting, if you don't have a dial on the breaker or a way for you to change that with a digital logic control trip unit or anything like that to a set value, then say you walk out to a motor case breaker and there's no instantaneous dial on it, you can test it at 8 or 10 times the long time setting or the frame rating of the breaker and see at what point does it trip. And typically with that, a tolerance can be anywhere between plus or minus 10% or plus or minus 25%. And you just want to make sure that it's tripping. Typically instantaneous will say under 5 cycles. But again, it's just you want it to trip as fast as possible. So now we're kind of look at so trip unit settings and how they affect the curve. So seen here pictured, we have a short time region circled, and we have a pickup setting of 6. So when you're reading a trip curve, the amps are always going to be on the bottom on the horizontal axis or the x-axis, and on the y-axis you're always going to have your time. So when we say pickup of 6, typically you'll have a value on the bottom of that trip curve that corresponds with 6 times. So you'll see here at 6, this is where the location of the curve is. Now, if we go and we change it to 2 for our pickup value, you'll see how the curve moved dramatically to the left. And that's because the current scale is on the bottom, so that's why it shifted left. And so that's how your trip settings kind of affect the curve and affect your time bands and everything like that. So now we'll look into how to test. So when testing, here I have a list of applicable standards and as well as recommendations for circuit breaker testing. A good rule of thumb is to always follow the NETA maintenance testing standards, as well as IEEE C37. NFPA 70B is also a good recommendation for circuit breaker maintenance. It has a listed schedule that we'll kind of look at later in the presentation as far as when you should test, how often you should test. And they also have like an evaluation part as well for, how critical your circuit breaker is, which we'll get into later. So when going through inspection procedures, this will be like your visual inspection, okay? You're checking the temperature check of the breaker. For that, you can use like an IR camera if you want to do that externally, or you can pop open the switchgear, take a look at the breakers themselves, see if there's any burn marks, any damage to any contacts, anything like that. You want to inspect the enclosure, make sure there's no evidence of overheating, not too much dust collecting. If you can, keep everything clean. Make sure that the electronic trip unit, you can check that, make sure that it's set properly. If you have a secondary injection test set, you can use that. You also want to check for any faulty wires, if there's any tearing of the insulation, anything like that. So another testing method that you do that we mentioned previously, again, your insulation resistance test. So now we're looking into, okay, how are we going to perform that test? So again, it's determining the adequacy of insulation between, again, your pole to pole, phase to phase, and phase to ground. And so when doing these tests, a high resistance is a green flag, okay? Now, the voltage is gonna depend on what standard you're following and what rating the breaker is. So typically, NEMA AB4 recommendation for molded case breakers will recommend you test with at least 500 volts DC, but the more voltage you use, up to 1,000 volts, will give you a little more accuracy, as well as what resistance you should expect. And then also NETA, we have a recommendation here of 1,000 volts minimum with a minimum reading of 100 mega ohms for your airframe breakers. So when doing this, the circuit breaker should be removed from the equipment for this test, and it needs to be isolated safely. And it needs to be performed with this. It can also be performed when the circuit breaker is in its equipment. For that, you'll just have it in the test position. So there's different positions that you can have a breaker in regards to switchgear. You can have it in the test position, you can have it in the connected position, you can have it completely removed. So just having it in the test position, as long as it's isolated, you're able to perform this test. Another test that we mentioned, contact resistance or individual pole resistance. So again, this is checking the integrity of the contacts and your internal connections. So when doing this, you want to make sure that you have a low resistance, which again is going to be typically determined by the breaker manufacturer. They'll kind of tell you in the manual what to expect in regards to resistance value for the contacts. The lower resistance, the better. Again, you want to allow for ideal path for current to flow through. You don't want to have much resistance, so you can get the maximum current or you want to get the correct current flowing through the breaker. You can also perform a millivolt drop test. So with that, that's typically going to be done on molded case breakers using a supply of 24 volts DC or less. And you're typically going to apply the actual rated current of the breaker. So if you have an 800 amp molded case breaker, you want to apply at least 500 amps of test current to perform a millivolt drop test on that. Now, for your airframe breakers and other smaller rated breakers, you can use a DLRO. And just depending on the rating of the breaker, you can use either a 10 amp or 100 amp DC resistance tester. So with these results, again, you're checking the contact integrity throughout time. So you can trend these results over time to just make sure that they're comparing to whatever the manufacturer's standard is. So where do you make these connections when testing the breaker? So you'd actually connect right here on the terminals of the breaker that you see pictured here. And you're really just, again, measuring the contacts, measuring the path of current, making sure that um, that there's small that it's a small resistance that you're measuring, because a high resistance is going to impede the flow of current. So now you're looking at how to test. Okay, so here we have a few safety procedures for removal and testing of circuit breakers. So listed here, we have operate the breaker to the off position, turn off all power supplying the breaker, and electrically isolate it from any other circuits. You want to make sure that all incoming power that's on your line side is going to be de-energized. And then you want to use properly rated test cables when connecting to a test set. So that's important, because if you use a smaller gauge wire as you're performing primary injection, that can heat up and that can actually burn through the insulation if it's not properly sized. A way to overcome that, if you have just smaller wires, you can actually parallel those wires and have multiple current paths. That'll allow you to get the higher current you need without having to have a overly sized wire. Typically with that, the reason we say size the wires correctly is because you don't want to have too much impedance as well. So again, if you think about it like water, if you have a larger pipe, it's going to allow for more current to flow, more water to flow, right? So that's exactly why the properly rated test cables is important. You also want to make sure all test connections are properly torqued and secured. So again, when you're injecting this 20,000, 10,000 amps or more, typically you're going to see those cables jumping, the test sets jumping, the breakers jumping, everything's going to be jumping. So you want to make sure you have everything secured, all your connections tied down so there's no arcing. You also want to make sure, if possible, you can have the breaker strapped to either the pallet or the raised stand that it's on, or the test set itself, just to make sure it doesn't blow off and cause any danger to those testing. So here we're looking at a few tools that you'll need to test. So pictured on the left, we kind of just have an example of a power supply, whether that's building power, 480 volt, 240 volt, whatever, or a generator power. Then you'll need cables to connect that to whatever test set you're using. On the bottom left, you're going to need a ground connection for your test set for safety, as well as a ground cable. You'll also need an interface for you to use when controlling the primary injection test set, whether that's a legacy test set where you're using a PLC controller, whether that's manual control, or whether that's digital control as seen here with the computer. You also need a method of connecting to the breaker, whether that's bus bar connections or whether that's cable connections, and then the breaker itself. A quick note here is, okay, well, how would you size a generator? So again, a lot of times you're out in the field, you're using generator power to power these primary injection test sets as you go and do a job. So here we just have a quick list of what you can do as far as how to size your generator properly. Basically, you want a list of all the items that are going to be powered with that, whether you're powering a single primary injection test set or different appliances. You want to determine the energy you need to turn those on, as well as the running energy you need to operate it. And typically for those, they're going to be on the equipment itself or in the owner's manual. From there, you'll calculate your total power requirement, either adding those up in kilowatts or kVA. And then for that, again, you can convert that to watts. And then from there, you'll know, okay, I need this big kilowatt generator, or I need this much, again, kVA, same thing. And so after that, now we're going to go ahead and look at connecting to the breaker, right? So we know what tools we need. We'll know how to go and get what generator, what power supply we need. Now we're going to connect to the breaker. So pictured here on the top, we have cables that we use. Again, there's 3 cables each wired together, so that's providing 3 paths for the current for each connection. That's just basically letting us use a smaller gauge cable to get a little bit higher current. Or you can use bus. Typically, you'll hear them referred to as stabs if you're actually pushing a draw-out breaker onto them. But you can use any assortment of bus to connect to breakers, and we'll always recommend bus because copper, metal, and getting more surface area is a lot better connection than using the cables themselves because of the impedance. So here again, we have an example of how you can overcome some impedance in regards to cables. So cable impedance is a big factor when performing primary injection. The longer length cables you have, the further the current has to travel, the more impedance it's gonna have. So one way you can overcome that is you can actually twist the cables and kind of cancel out some of that impedance, or again, providing more paths of current. So multiple parallel connections. But again, your input length to the test set itself, your input power cable connections, as well as the output connections to the breaker. You want to make sure that you keep those as short as possible, because again, the longer they are, it's going to affect your output of your primary injection test set. Okay, so now after we've considered all that, now we're going to actually run the test. So when running the test, again, you can either be using a smart primary injection test set that uses software, or you can be using a legacy test set. Either way, you can get the job done. And just seeing here pictured, you can either have a digital curve library, digital reporting, or manual reporting. So now we're going to go ahead and go through kind of an example test. So for the people out there who, walking out for primary injection the first time, what should you do? What exactly is going through a test? What involves that? So, you walk out to the job site for the first time and you see, okay, hey, here's the breaker itself. So you take a look at the nameplate and you see it's a 1600 amp frame size breaker. Okay, you'll see that we're testing, and this is actually a breaker that we tested when we went out and demoed a test set. So this is, again, a real life experience. So this 1600 amp breaker, it didn't have a sensor plug in it. Typically sensor plugs you'll see in your molded case breakers. So it wasn't derated or anything. We didn't have to worry about that. It was 1600 amp frame size. So we looked at the trip unit. We're deciding, okay, is it a micrologic trip unit? Is it going to be, an AC Pro where we actually tell it, okay, how much current will trip, a long time? Do you type it in or do you actually have to set a dial? So for this breaker, we were setting a dial. And so we went through and we're like, okay, this calculation here on the left is how we found our test current. But how do I know what to look for on the trip unit to do that? Well, you'll see the first test we ran on this breaker was a long time test. So that's what this whole example is. It's a long time test, right? So when running that, we want to take a look at the long time settings on the breaker. For that, we had a long time delay and a long time pickup. Okay, so our long time pickup was 1.0 times IN, which is equal to IR. Now, again, IN isn't the rating of the breaker, but it's actually pictured here. IN is equal to 1200 amps. So that's why we use the value of 1200 instead of the 1600 amp sensor rating for the breaker. So we did 1.0 times 1200, and that gave us 1200 amps as our pickup current. So if you were trying to perform a pickup test on this breaker, using a primary injection test set, you would ramp up your current continuously up to 1200 amps. And at 1200 amps, you should see the indicator light here pictured on the bottom right kind of illuminate or start blinking. That's telling you that long time pickups, it's picking up that test current and it's going to get ready to start timing. So from there, using the previous standard recommendation of 300% or 3 times the long time pickup setting, that's why we did 3 times 1200 amps, which gave us 3600 amps. And that's the test current we would use for a long time when we're testing at 3 times. But you can always test higher than that. You can test 5 times, 6 times. All it's going to do is just affect the timing. But you just want to make sure that that's within the curve and you're good to go. If we were going to be doing short time, we would take a look at this section. So you'll see here it says S1. So S1, it just means 8. So 8 times IR, which is our long time pickup, that would be 8 times 1200 amps. And so that's how we would get our short circuit if we were doing that. Now, before we can test long time, on the previous slide, and I'll go back real quick, there was a ground fault setting. So if we were trying to run any of these other tests, it would be tripping on ground fault because that's typically at a lower test current. So in order to not do that, we need to overcome ground fault. So seen here pictured on the left, you have a couple different ways you can overcome ground fault. On your AC Pros and other micrologic trip units, you can turn ground fault off in the settings. You can also have a ground fault defeat plug, or you can short certain terminals. So again, with airframe breakers, with the breaker we were testing, we had kind of like a cheat sheet where we could actually short the terminals with a small wire here. And if you jumper those wires together, it defeated ground. And we found that out by shorting terminals N and G from the user manual of that breaker. And it told us that's how we could defeat ground fault, which is what we did. And that's what allowed us to test our long time, short time, and instantaneous settings. And then after we ran through those, we could move that wire off and test the ground fault setting. So again, we defeated ground. Now we went ahead and connected to the breaker. So we connected our bus, copper bus, to the breaker from the stabs or the output stabs of our primary injection test set to the stabs of the breaker. And seen here pictured on the right is the breaker under test. So from there, we went into the software and we requested 3,600 amps for our long time test. And we initiated that, and that's how we ran our test. It would stop, and then the current would be recorded and the time would be recorded. So now, okay, we ran through a test, but how do I know how to read a trip curve, right? If I don't have the software, how am I gonna go and manually figure that out? So here's kind of an example of how to do that. So again, your current's gonna be on the horizontal axis, right? So we know we had a long time delay on our trip unit of 24. So when looking at these different time bands, we wanna pay attention to the one that's marked 24, because that's the time band for that specific delay setting. So then we're gonna go ahead and look, okay, well, we know we were testing at 3 times or 300% of the long time pickup. Again, if you were testing at a different multiple, 5, 6, 7, whatever, then you would just kind of sketch that line down on that number instead. But since we were testing at 3, that's why we had the blue line sketched on 3. So then all we're gonna do is mark the intersecting points of the upper and lower limits of that time band, the one for 24. And that's gonna tell us when the breaker should trip. So you see here, we mark the intersecting points and it shows 160 seconds as pictured on the left axis. So now it's acceptable to say that at 3,600 amps test current for the long time setting, the breaker should trip between 160 seconds plus or minus whatever the tolerance is, which you can find that in the user manual. And that's how you would read the curve. So after you've gone through and you've checked everything, you made sure the curve checked out, now you would get your report. Again, you can have a handwritten report as seen pictured here on the right, or a software-based report. And the breaker should be replaced if the contacts are not open with the breaker in the trip or off position, if the breaker does not reset when you hit the reset button or when you're trying to close it, if the contacts are not closed with the breaker in the on position, or if the mechanical trip provisions, meaning if you manually trip the breaker, if it doesn't work, then you should replace your breaker. And if the breaker is just out of spec, if it's not conforming with the times that you have on your TCC curves, then you can always send it to get refurbished, checked out, or you can manually check it out yourself. You know, open up the internals. If it's an airframe breaker, take a look and make sure that there's nothing wrong internally with the contacts, anything's out of place, anything like that. And that could affect your timing as well. So now we'll take a look at when to perform testing. So when to perform testing, there's not a set time limit on when you should perform testing. That's all going to depend on the company that's doing the testing and the criticality of the instrument. So seen here, we kind of have a list of all the different factors that go into how often you perform breaker testing. Typically, you can refer to the manufacturer's recommendations of the breaker. So they'll provide guidelines as far as testing intervals and procedures and stuff like that. You can take a look at industry standards. So the standards we had previously and see, okay, hey, what do they recommend as far as how often I should test breakers? Typically, you'll see every 3 to 5 years as a requirement. If it's more critical, you'll say every 2 years, maybe every year. A lot of insurance companies will say, okay, hey, for ground fault testing, we want to have testing done every year, and we want to have documentation of that. And again, the reason for that is because a lot of faults that you'll see, typically ground fault will be the first fault that occurs before any other faults occur. Also, the criticality of the instrument or the equipment. So again, critical systems or those that are in high demand environments, they're going to require more frequent testing. The last thing you want is for a breaker in a critical environment to fail. So that's why you test those more often. Operating conditions, if the conditions are bad, if they're subject to extreme heat or anything like that, then you want to test those more frequently because those have higher risk of failure. Historical performance. If a breaker is known to have any nuisance tripping or any issues with malfunctions or anything like that in the past, then again, you're going to test more frequently. And then any local regulations and compliance and stuff like that. So when looking at some of the preventative maintenance, some of the stuff that you can look visually and see. So with motor case breakers, you know, you can see if there's any dust, dirt, soot, grease, or moisture, any wire damage. Again, you can check the trip units, wire connections. For your airframe breakers, you can check the arc chutes, inspect the breaker contacts. And then one way you can actually, you know, check the breaker contacts and make sure that everything's touching correctly, everything like that, you can open up the breaker and do what we call a slow close, where you kind of grab the contacts of the breaker, you move it close slowly and make sure that everything kind of connects in the correct process. So here we have visual inspection requirements. So again, we got this from NFPA 70B. And this is just telling you a few of the visual inspections that you should perform on the different types of breakers, whether they're molded case breakers, insulated, or your low voltage airframe breakers, right? So seen here, again, your arcing contacts, and then your chutes and everything like that, that's not gonna be applicable for your molded case breakers. But then you're also gonna have just different things you do for different types of breakers. So again, this can all be found in that NFPA recommendation, just to give you an idea of exactly what you should be doing for each type of breaker. And then also here, again, this is kind of like a maintenance interval schedule for when you should be performing those visual inspections, or the electrical testing. So again, that's your contact resistance, insulation resistance, and your primary injection. So again, if they're real critical pieces of equipment, real critical breakers and real critical applications, those would be classified as condition 3. So you'll see those tests are frequently done every year or more. But again, in that NFPA 70B recommendation, they have like a condition assessment that you can do, kind of seeing, okay, how crucial is this equipment? How new is this equipment? What condition is it in? Stuff like that. And that'll kind of determine how often you should be testing. There's not really a set interval for breaker testing. Common rule of thumb is, hey, every 3 to 5 years. Typically, you'll see now breakers out in the field, you'll have a sticker for NFPA rating and ARC rating, making sure that they're tested every 5 years. Again, you can have ground fault testing every year, or you can just perform every 2 years as like a rule of thumb. But again, it's all going to depend on the company, the manufacturer's recommendations, and just different aspects that can affect when you should test. So again, in summary, these breakers, again, are the insurance policy of your protection system. If anything goes bad, anything goes wrong, there's a high fault current, you want to protect your most critical assets, and that's what the breaker is designed to do. So you want to make sure that it operates when needed. And so to do that, you have to perform routine maintenance and make sure you inspect it accordingly. Main tests done on low voltage circuit breakers, again, your primary injection, your insulation resistance, and your contact resistance. The biggest hurdle, again, is understanding those time current curves. Again, in order to actually test the breaker correctly, you have to be able to read those curves. And then just understanding the breaker trip units, how to find your test current, everything like that, that can help you go a long way as far as testing in 5 to 10 minutes a breaker versus 30 minutes to an hour a breaker, right? Just the understanding of it. With that being said, we're going to take a quick look at the Megger's offering for primary injection testing. And this is our newest test set, SPI 4000. So this SPI 4000, again, it's a high current primary injection test set, capable of testing low voltage breakers, switchgear CTs, reclosing circuit breakers, and molded case circuit breakers. So a quick overview of the unit. You'll see in here pictured on the left, you have the output stabs as well as a measurement portion. On the right, you'll have the input power, as well as the manual on-off breaker. And then you have an emergency stop, output indicator, and an Ethernet port for communication to an external PC. You also have a 120 volt outlet. You'll have wheel stops, and then wheel locks as well. So again, the SPI 4000 is part of our SPI family. So when we say SPI, we mean Smart Primary Injection. So that's just going to be all software based, right? SPI 4000 is rated for testing breakers up to 4,000 amps. The 225, it's rated for testing breakers up to 225 amps. But those can be put in parallel to get a higher current output if needed, up to 4. So SPI 4000, the reason that it's such a hit right now, again, is the size of it. So it's roughly half the size of the older legacy test sets that we were mentioning before. So seen here pictured on the top right, you'll just see smaller 1600 amp rated breakers right next to the SPI 4000. So its output through a breaker has been tested to be 40,000 amps. If you dead short it, it can be higher than that. and then it weighs 514 pounds. So that's roughly 80 amps a pound. And so again, that's great for shipping and DOT restrictions. You don't have to have an employee be licensed to drive a box truck or anything like that. Shipping wise, you know, it's going to be less hassle and less cost on the user. And then seeing here, we have it in the back of a van. All we had to do to put in the van was pretty much use 2 ramps that we ordered on Amazon, use an electronic winch and just wheel it up there. And then we strapped it in and it was good to go. And seen here again, it's just a comparison of a legacy test set to that SPI 4000. Again, the legacy test sets were roughly 1,200 pounds. SPI 4000 can pretty much fit inside the legacy test sets. And so these are great when going in data centers or just going in smaller switchgear rooms where they can fit right through the door. You don't have to worry about having a secondary access or, anything like that. And then again, like we talked about, the biggest hurdle again is going to be those time current curves, understanding them, reading them. So when you have new trainees and everything like that, you want to be able to have all those curves generated to where they can just look at it and say, hey, it's plotting it for me. I know where it tripped. I know if it passed or not. So that curve library is actually part of the software for that SPI 4000. And this software has full integration with PowerDB as far as your reporting and everything like that. So as you go and you do the testing, it'll populate all the results live to PowerDB if you have it open on the side. And so when you're done with your test, you don't have to go and retype in those values. They'll be there already populated. And with that, that concludes the webinar. Again, here's contact information for technical support as well as my email. If you have any questions, feel free to contact me. But now I guess we'll open the floor up to questions, Griffin.
Alrighty. Thank you so much, David. At this time, the presentation portion of the webinar is officially concluded. We will now take some time to answer as many of your questions as possible. Please remember, if you do have questions, please submit them to the Ask a Question window. For those of you that are leaving, please be sure to fill out our survey before you head out. We would greatly appreciate if you could take a couple of minutes to provide your feedback so that we can continue to improve upon our future webinars. On the survey, there's also a field where you can request a demo or quote for any Megger products if you're interested. A copy of this presentation, your certificate of attendance, and a link to a video recording of this webinar will be emailed to everybody in about 2 business days. The link that you use to join into the session will bring you to a recording of the webinar in about an hour after we wrap up here. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars. Be sure to register for our next webinar on February 16th, titled Advanced Partial Discharge Diagnostics of Power Cables Using a Damped AC Voltage Source, and that'll be presented by our own Jason Aaron. Alrighty, now let's get to some of your questions. Our first question is going to be for Nadozi. It asks, is there any advantage to testing all 3 phases at the same time rather than 1 phase at a time?
When you're doing primary injection testing, you want to test each phase independently. The only advantage you might get by trying to inject in all 3 phases will be to save time, but that's not the right way to test it. The reason is because you want to see the pole-to-pole operation. You don't want A phase to trip and B phase doesn't trip and C phase trips. You wouldn't know. So you want to record the time for each phase. The whole idea is to test through the breaker. So if there's a contact issue on A phase, but it's not sure, but the B and C phase is good, you wouldn't catch that if you did a whole 3-phase injection. So that's why you test pole-to-pole, to make sure you don't have a pole-to-pole discrepancy. In practical, when you're doing primary injection, you go phase to phase, and each primary injection unit would always have an output source and a return per phase. So you're always doing 1 phase first and the other phase second and the 3rd phase, and you're getting the results for all of that. I hope that answers the question. Thanks.
Excellent. Thank you so much, Dozy. Our next question is for Swapnil. It asks, is there a limit on size of a breaker when doing the testing? And the range that they're referencing is 50 amps to 100 amps.
Thanks, Griffin. So on that question, it's going to be like 2 answers instead of 1, because they're going to be, I don't know what breaker we are talking about. Are we talking about the breaker which is on the input side or the source side, or the breaker which we are testing? So I'll answer it in 2 sections. So if we are talking about the breaker which we are testing, we are definitely 50 amp and 100 amp is not a big amperage rating for testing, but definitely we can test those sizing on or breaker sizer. if we are talking about the source breakers or the input voltage source amperage breakers, it totally depends on what type of test equipment you are using or what type of primary injection test you are using on the amperage side. So if you're using a very high amperage output test equipment, for example, the SPI 4000, which is a 40,000 amp unit, so in that case, it is just a load to the source. So it's gonna pull all the required power to supply or to inject the necessary amperes on the breaker which we are testing. So in that case, we not only require a very high ampere input breaker, but we also require a very high voltage. And just to give an example on SPI 4000, for for that particular equipment, we need around like 480 volts input as well as minimum of 225 amps of breaker. So I hope that answers that question. Thank you.
Yeah, and Swapno, just chiming in real quick too. On the next slide here, I actually have some of the specs of the SPI 4000, which can kind of help that out.
Yeah.
Excellent.
Thank you.
Thank you both, Swapnil. Thank you, David. All right. So our next question here, and forgive me if I butcher it a little bit, but they ask David, I have a 2000 amp rated breaker with 1200 amp trip setting. So if the long time test is 3 times that, it's 1200 amps, times 3 is 3600 amps. Is that harmful to the breaker? I understand that it's for a short period of time.
Yeah, so it won't be harmful to the breaker. You're testing at under what it's rated for. All it's gonna do is if you run it for super long, you might see some smoke. That'll just be the dust kind of burning off. So for your 1200 amp trip setting, again, your long time setting could be 1.0. So 1.0 times 1200, that'll be 1200 for your pickup. And then you times it by 3. So that, yes, you're correct for the 3600 amp. It's not going to be harmful to the breaker. Again, these breakers are designed frame size wise to handle, 100,000 amps instantaneous, 65,000 amps instantaneous. So it shouldn't be harmful to the breaker if it's a 2000 amp breaker.
Excellent. Thank you so much, David. David, would you mind answering our next question? It doesn't look like we have it assigned to a person, but I'm going to go ahead and ask it to you. They ask, what is the maximum voltage rating for performing primary injection testing?
So for voltage rating, it's not too much as far as a maximum voltage rating for performing. I mean, you can say like don't go over like you can say like a limit, like 24 volts DC, right? But then again, it's like, okay, well, that voltage is all dependent on how you're getting the output, right? Because the way these things work, they take input power, they have a transformer inside, and they step it up. So in order to do that, you have to have a really low voltage to get that high output current. It's just an inverse relationship. So you're typically with these test sets, you're not going to exceed 20, 24 volts compliance voltage when you're connected in series. In parallel, since you want more current out, that's going to be even less. So that's why you'll see techs out in the field say you can go and actually grab these cables as you're performing these testing, which is not what we recommend, but it's because of the low voltage being pushed. You don't have to worry too much about the voltage rating because all primary injection test sets are going to be using a low compliance voltage typically.
Understood. Thank you so much, David. Our next question is going to go over to Swapnil. It asks, would you conduct primary injection testing before energizing a brand new MCC low voltage breaker? And then they also ask, what is the minimum circuit breaker size that requires primary injection testing?
So on the MCC panels, there could be breaker sizing ranging from very low amperage, like around 100, 125 amps to very high, around 2500 amperes. It all depends on the type of motor and the type of load. But then if it's a critical application, of course, we would recommend to at least test the high amperes or the low voltage breakers on that part, around 1000 amps if it's more than 1000 amps. If your institution or organization wants you to test all the breakers, you would have to test all the breakers in the MCC panels. But there are no specific guidelines on the sizing of breakers related to MCC that on what type of breakers should we conduct the testing on. But if it's critical application, definitely we would recommend that.
Awesome. Thank you so much, Swapnil. Let me get my bearings real quick. Okay. Our next question, we're going to go back to David. It asks, can a 13 amp socket outlet power up the SPI 4000?
So for the SPI 4000, this one will work off 200 volts input power, 240 or 480, or generator power. If you wanted a power a primary injection test set off, 120 volt outlet power, we have the smaller SPI 225 that can work with that. But for this test set to get the output current required, you need at least a 208 volt minimum.
Gotcha. Thank you so much, David. Looks like our next question is going back to you as well. It says, where do you find the TCC curves if the breaker manual is not available?
So that's a good question. We were actually out on a training yesterday, and so they didn't have the breaker curves. It was a test breaker that they found lying around somewhere in their garage. The way you can do that, typically on every breaker, there's going to be a cat number. So if you type that cat number in online and you just type in datasheet, after it, typically you'll be able to find a few different sites where if you go through and you search through them, sometimes you'll find a PDF of a data sheet for that trip unit or for that breaker, and then you can find the trip curves on there. That's typically the best way to go about doing it, because a lot of times, especially with breakers that are, ancient, you won't have any luck finding trip curves, but that'd be your best bet if you don't have one on hand.
Thank you, David. Our next question, would you mind answering this next question for me, David? It asks, what is the smallest size breaker that's required to be primary injection tested?
For that, you can test motor case breakers all the way down to 10, 5 amps. It's all going to depend again on what you're trying to get out of it. Are you trying to test it? Is it a critical application? What does your company want to do? Now, most of our test sets can test breakers all the way down to 30 amps or less. The SPI 225 again is designed for that. SPI 4000 can go all the way down to 30 amps, and it's been fine testing. Required, it's just going to be dependent on what the breaker manual says, whether it recommends you to do primary injection or if it recommends you to just test contact resistance. It depends on what the breaker manual says.
Good. Thank you, David. Our next question is going to go to Nadozi. It asks, how do you test contact timing for low voltage breakers for open and close times when the breaker is only manually operated?
So contact timing is typically a test you do on medium voltage and high voltage circuit breakers. You don't perform that on low voltage circuit breakers. On low voltage circuit breakers, we're performing primary injection to test the trip times. We want to see how quickly it could trip if there's an instantaneous fault. So like a short circuit fault, we want to see how quickly the breaker would trip. And we also want to see how the breaker would trip if there's a long time fault. So there's an overload. You don't want it to trip immediately. Say, for example, you're using the blow dryer at your bathroom. You just don't want the breaker to trip because the load suddenly just went over the actual rate, and you want to give it a long time for it to see that overcurrent before it trips. And a short time in the sense where you're going to start up a motor, there's going to be high inrush current. You don't want the breaker to trip. You want the breaker to, for a short time, allow that current to pass through. So when you test low voltage circuit breakers, you're doing a injection test to verify the long time, short time, and instantaneous, and also the ground fault, and comparing it to the breaker curve. Whereas timing a circuit breaker contact is different for high voltage, is usually applied in medium voltage and high voltage circuit breaker. You want to see how quickly the open time is and how quickly the close time is. Whereas low voltage circuit breakers are totally different. So timing in the sense of contact timing wouldn't apply for a low voltage circuit breaker.
Good. Thank you so much. All right, Swapna, we're going to you for our next question. It asks, how can we test timing test of the circuit breaker with this device that we talked about? I believe they're referring to the SPI.
Yeah, so this aligns with the same question, the previous question, and the answer is exactly what Dozy answered. Like probably they are thinking about the timing test, which is usually done on a medium voltage breakers or high voltage breakers. When we talk about primary injection testing, we are talking or specifically talking on low voltage circuit breakers. And like Dozy mentioned, we are just looking for long time, short time, instantaneous, and ground fault testing on low voltage. The timing test, which the audience is referring to in this question is more related to medium voltage and high voltage breaker, which is a totally different part of testing.
Thank you so much, Swapnil.
Yep.
David, we're going to go to you for this next question. It asks, do you have any input on performing contact resistance on a breaker? Is there a preference between using DLRO or using the multi-volt drop method?
So with that, it's all going to depend on what test equipment you have. If you have a small primary injection test set that can only output 200 amps and you're testing a 200 amp breaker or a 300 amp breaker, sorry, and you can't perform a millivolt drop test on it because you can't test it at that 300 amps, then you can use a DLRO if you have one on hand. Now, say you have a DDA and you're testing a 4,000 amp breaker. Well, you can perform a millivolt drop test because the DDA can do that. And so you don't need to go and find and reach for your DLRO because you can perform a millivolt drop test with that. You know, using leads to measure the voltage drop, you know what current you're injecting, and therefore you can calculate the contact resistance. With that being said, it's always a recommendation for molded case breakers to be millivolt drop tested. That's typically, you know, a common rule of thumb. Now, your DLRO can still test your contacts, can still test airframe breakers fine. In regards to what current you should be using, you can use 10 amps for, I think, breakers rated under 500 amps and less, or 100 amps for breakers 500 amps or more. I might need to double check that as far as standard, but I believe that's right. Dozy, if you want to chime in on that.
Unfortunately, I think Josie had to drop off for today because we are actually running out of time for our Q&A session. Sorry, we had a lot of wonderful questions come in today, but not enough time to get to them. Do not worry, we will answer anything we didn't get to offline via email. So we will be working up to follow up with all of you. As a reminder, a copy of your presentation, a certificate of attendance, and a link to a video recording of this webinar will be emailed to all of you in about 2 business days. Thank you all for attending today. After we conclude here, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested, and a field to let us know how we did and what topics we should cover in the future. Once again, I'd like to thank you all for attending, and have a great weekend.